Vishal Garg. He is professor and head of the Center for IT in Building Science at IIIT Hyderabad. His current research interests are in areas of smart energy homes, building energy simulation, and cool roofs. Coming from engineering background, he has Ph.D. from the IIT Delhi. Dr. Vishal was founding president of the Indian chapter of the International Building Performance Simulation Association. He is a fellow of IBPSA and recipient of inaugural Arthur H. Rosenfeld Urban Cooling Achievement Award. Today, Dr. Vishal will give us a brief view on personal environment control and demand response. So, delegates, let's welcome Dr. Vishal.
I am going to give a brief presentation on our research in the area of task control and how we can use task control for demand response and include the occupants in the demand response action. So basically, we know that when there is a need for demand response, when there is a demand response event, we need to reduce our demand. And there are a lot of ways people try to achieve it. And it can be either shutting down a particular service, say for example, air conditioning in a building, or changing the set point so that the load reduces. In case of air conditioning, the set point can be increased. Sometimes we shut off some buildings in a group of buildings and try to reduce the demand. So there are various ways this is done, but mostly it is done at the building level and the building manager decides what is to be done and the users have no control. Many times users even don't know that demand response event is there and they are expected to reduce their loads. So let us see how we can bring individual users in this demand response event, and they participate and collectively we try to reduce the demand in the building while maintaining preferred comfort levels as per each individual. So it's very common to see that when multiple people are occupying any space, some people find it comfortable, some people don't find it comfortable. Same temperature, same conditions, some people may complain that it's a little too hot and some people may say it's a little too cold. So different people have different thermal requirements, even when the conditions are same, but because the requirements are different, they might perceive the space to be either too hot or too cold. Other times, the actual conditions might be different in the building. So here you can see that some part of the building or the space rather is warmer because of the solar radiation entering from the window, and the other parts, the core part, the inside part of the space is cooler, and therefore people sitting next to the window would complain that it is too hot, and people sitting inside the core would say, that it's a little too cold. So there can be a non-uniformity of temperature in the space. So how can we deliver personalized services? It's not just air conditioning, it can be lighting also, it can be any other service that an occupant would like to have, and the occupant would like to have personalization over his or her space and control the parameters of these services. So how can we do that? So there's a lot of work going on in this area, and this is called personal comfort systems. And here you can see some pictures. You can see that there is a table fan, there is a light beneath this cabinet, that's the task light, there is a foot warmer. So different kind of devices are being developed which can help people control the conditions in their task environment. There are also chairs which are developed which can have their own heating element. They can have a fan also, so the chair which will keep you cool or would provide you warmth when it is winters, and then it can have its own control unit so that you can control the air velocity or the temperature. Then there is convective, there is a floor radiant heating systems where through the floor radiatively the body can get heat. And again, we can sometimes not only give heat, we can also give cooled by having chilled water running into these panels and provide comfort to the user. So there are so many different ways people are developing personal comfort systems. A lot of cutting edge work is happening at the Center for Built Environment in Berkeley in US. So the issue is that if we want to provide everybody some kind of personalization over the environment, we need to do local sensing. We need sensors in each of these spaces to measure what is the temperature, humidity, whether the space is occupied or not, if the person is getting glare or not. We have to understand what are the loads that are connected. Suppose somebody has connected a computer, a laptop, a monitor, or coffee maker, or any of such devices there. Then we have to make these talk to each other. We need communication framework so that within the task, these elements can talk to each other, and they can talk to the space conditioning system also. So like the task light, the table lamp is talking to the lamp on the ceiling in the space, and that is then talking to the BMS. And then the user has interface through which the user can get the feedback, can monitor what's happening at the space, and also control. So there's an integration required between the task and the ambient. So what is the benefit? We can provide individualized comfort. When people are getting individualized comfort, they are more satisfied with the environment, and their productivity is expected to be better, and it can lead to energy savings and also good demand response. So like here you can see in this picture that there are cold spots as well as hot spots. So there's nobody sitting here. So this is warm space. So it's like a micro environment, it's like a bubble. And the space, this micro environment or bubble is controlled by the user. So we don't have to cool the whole space. We can have spot cooling and we can save energy. So how we are doing, we have a radiantly cooled desk. In this case, it is also having partitions. It's a cubicle. So chill water enters this cubicle, and the cubicle transfers the heat to the user through radiation. So the user can control how much should be the temperature of this partition, and can control the the cooled the cool that the person is getting there. Then there is a smart hub. This hub gives control over the task environment, and I'll show you how this whole thing works. And the user can then decide how much heating, how much cooling, how much lighting, how much power the user needs. And when there is a demand response event, the user can reduce the requirement and participate in the event. We also have a US patent on this mechanism of demand response at the task level. So let us see what happens during the demand response event. There are two ways demand response event can happen. One, when there is no limit to the power supply, you can get as much power as you want, but you have to pay. So this is time of the day tariff or variable tariff. You pay more at certain times of the day. Other kind is where the limit is there on the power, irrespective of the cost the one is willing to pay. This is the load available. This is the load that can be serviced, and the cost is fixed. So we are going to talk about the second one, where there is a limit on how much load can be put onto the system. So let us say there is a campus, there are a few buildings, there is a solar PV of 600 kilowatt, there is a diesel generator of 1400 kilowatt, and there are 4 buildings, and the total load of these 4 buildings is equal to the generation of 2000 kilowatts at a given time. Now this is right now grid islanded. There is no power available from the grid, and the generation is happening on site. Now assume that there is a decrease in the solar radiation, and therefore the generation reduces from 600 watts to 400 watts. Then what will happen? Now every building will get a new target. So instead of 400 kilowatt, the building number 1 has to now consume only 360 kilowatt. The building that passes this message to each floor So each floor now gets a target. That means each floor is a tenant, say for example, is another company or an entity, they get their own targets. And then those targets are transferred to the individual users. So every user will now get a target to reduce the energy consumption through the smart hub interface. Now here the user gets the warning that you are consuming more and your target is 300 watts, you are consuming 400 watts. So user here selects to reduce the air conditioning. So air conditioning load is reduced, the fan speed increases to provide a little bit more comfort, and the consumption goes down to 300 watts. In this case, the user doesn't want to compromise on thermal comfort. The user selects to reduce the plug load. So when the plug load is reduced, the laptop charging stops, the battery is used for doing the work, and the user is able to bring down the load. Now let us see the third scenario. In this case, there is a power user, and this user doesn't want to reduce anything, doesn't want to compromise on lighting, doesn't want to compromise on air conditioning, buy some more, is willing to pay. And then there is this person who is willing to share her load. So this person, instead of 300, now gets a lump of 600, and the other person takes a break, can go for a coffee or something. And the idea is that in a small time frame of 5 minutes, can we reduce the demand by 50% with everybody's participation and everybody deciding what preference they want for their comfort. So that's all what I wanted to present. I thank my colleagues and collaborators and Department of Science and Technology for funding this project. Thank you.